Hey everyone, welcome to This Explainer. All right, let's jump right in. Today we're going to tackle one of the most fascinating challenges in software architecture, how we actually take static UML diagrams and transform them into living, breathing, dynamic object-oriented code. We're talking about looking at a set of lines, boxes, and symbols and instantly seeing the exact loops and decisions that will eventually power an entire application. It's kind of like reading the Matrix, and by the end of this, you're going to be able to do exactly that.
So here's our roadmap for today. First up, bridging diagrams in code. Then we'll tackle iteration, basically modeling loops, followed by branching, which is how we model decisions. And finally, we'll bring it all together into the final code blueprint.
All right, Section 1, Bridging Diagrams in Code. You know, the main challenge we face as architects isn't just figuring out what a system should do. The real trick is communicating exactly how it should do it, using tools that, well, literally just sit there. They don't move, and they certainly don't compute. So the big question is, how do we turn these static pictures into dynamic systems? When you look at a blueprint for a house, you see where the plumbing goes. But when you look at a software blueprint, you somehow have to capture moving, dynamic logic. You have to capture actions that repeat over and over, or paths that diverge based on very specific user inputs. And that brings us to the core divide. On one hand, you've got your static UML diagram, the visual blueprint with all its symbols, stick figures, lines, the whole shebang. On the other hand, you have the dynamic logic, the actual running code that executes loops and if-else decisions. Now, we use the word blueprint for a very good reason. These aren't just back-of-the-napkin sketches. They are literal, highly specific instructions for constructing the building blocks of your code. Every single arrow, every bracket, they all have a precise translation.
Moving right along to Section 2, Iteration, or modeling loops.
So in the language of UML, showing iteration, or a loop, is actually incredibly simple. You just use an asterisk. We call this the iteration specifier. It basically taps the developer on the shoulder and says, hey, this specific action, yeah, it happens multiple times. And what's really interesting here is that there's no super strict rigid syntax for the clause that comes after it. You can totally use actual code or just pseudocode. Oh, and quick side note, if you ever need to show messages firing off simultaneously in parallel, you just use an asterisk followed by 2 forward slashes.
Let's actually see this in action. We've got our system user here, an actor we're calling the registrar. Now, the registrar wants to print out a list of courses. If we follow the flow, the registrar sends a print courses message to the registration manager. But check out the message going from the registration manager to the course object. It says 1.1, asterisk, bracket for I equals 1 to n, bracket, colon, print course of I. Boom, there's our asterisk right there, paired perfectly with a bracketed clause that defines exactly how the loop is going to run.
Okay, time for the magic trick. How does that visual translate to the keyboard? Honestly, it's practically a one-to-one mapping. The UML syntax 1.1 asterisk for I equals 1 to n translates flawlessly into a standard for loop. In the actual registration manager class code, it just becomes for I equals 1 to courses.size print course I. It's wild when you think about it. That tiny little asterisk acts as this massive directive, generating a whole block of iterative logic.
All right, Section 3, Branching, or modeling decisions. So we've got loops down tight. But now, we have to tell the system how to make decisions. Like, what happens when our registrar tries to actually register a student for a class? And I want to pause here for a second and validate something that developers and architects complain about literally all the time. As the source material emphasizes with a giant starburst, it's hard to show branching clearly. And yeah, it really is. Trying to capture a complex, multi-layered if-else decision tree on a flat 2D diagram without making it look like a messy plate of spaghetti? It's notoriously tricky. But, thankfully, UML gives us some pretty clever workarounds. Enter the guard condition. Let's look at this communication diagram, where the registrar is trying to register a student named Jim for a UML course. Notice messages 1.3 and 1.4. See the word found in brackets? Message 1.3 says bracket found, bracket register student. Message 1.4 is bracket exclamation point found, bracket error. That bracketed word is essentially your gatekeeper. It prefixes the sequence number and dictates that the sequence only continues down that specific path if the guard condition is completely met.
But what exactly is found? Let's break down the logic behind that guard condition. In our model, we're defining found as true only if both the student and the course actually exist in the system. So, in code syntax, that's student does not equal null and course does not equal null.
If Jim is in the database and the UML course is in the database, well, found equals true, and the registration proceeds smoothly. If either one is missing, found is false, and the system throws an error. It's a binary fork in the road, and it is captured entirely by those little square brackets.
Now we can also use an alt frame and a sequence diagram to show this exact same logic. See that large alt box at the bottom? It literally creates an if-else container. The top half shows what happens if our guard condition is met, we register the student. And the bottom half, separated by that dashed line, shows the else condition, we throw an error. It's the exact same branching logic we just talked about, just viewed through a totally different architectural lens.
Which brings us to Section 4, the final code blueprint.
Okay, so we have loops, and we have branching. Let's see how this fully constructed logic looks in actual code format. We're going to walk through the logical flow of our final register method, step by step, tying it right back to the registrar's journey. Step 1. The system executes find student looking for Jim. Step 2. It executes find course looking for UML. Step 3. Our guard condition kicks in as an if statement. So if both the student and the course exist, meaning neither is null, it executes course.registerStudent. Step 4. The else branch. If either is missing, it prints an error. This entire flow was perfectly dictated by the diagram.
To sum up the direct translation rules we've explored in this explainer, when you see an asterisk on a diagram, you immediately translate that into a for loop, or some iterative block in your code. When you see square brackets with guard conditions, or an alt frame, you're looking right at your if-else logic. And those stick figure actors, they're your external triggers initiating the public methods of your core classes.
I want to leave you with this final thought. Think about all the headaches of debugging. If a single missing bracket or a flawed if statement can completely break an entire code base in production, how much time and money does a perfect visual blueprint save your engineering team? By mastering how to translate these UML diagrams, architects and developers can spot logic flaws, infinite loops, and totally broken decision trees long before a single line of actual code is ever written. That right there is the true power of a blueprint. Thanks so much for joining me on this explainer, and keep learning.